Hello everyone! Today I would like to explore with you another fascinating phenomenon involving the interaction between electromagnetic waves and matter. And in particular, I would like to discuss what happens to a plane wave as, say, it's propagating through a medium up here, and for simplicity we assume that this medium is simply air. As it meets a thin film made like filled with a medium which we assume have a refraction index bigger than the one of air, meaning bigger than 1. And then, just for simplicity, we assume that on the other side of the film there is still air. Now for this video I will assume some familiarity with the basics of reflection and transmission. And those allow us to see something very simple immediately. So we know that part of this wave will be reflected in such a way that this incident angle, theta I, and this reflection angle here must be the same. And then we will have a transmission here. And as we get to this point, we will have another transmission, but also another reflection here. And at this point, we will have another transmission and other reflection. Now, I put a few dots here because this, in principle, can go on for forever. But for today's discussion, I would just like to focus on those two very fascinating reflected waves. Let me call them 1 and 2. That get together in this region of space coming from the same, like originating from the same original plane wave that we were studying, but getting there through different paths. And I will assume also some basic knowledge about interference, in particular constructive, destructive interference. And we know that when we have like a common source and different paths, then we are in the textbook situation for interference. And so it's very interesting to see, if we are an observer over here, to study the interference pattern here. What do we see? Do we see constructive interference, meaning like the maximum intensity that we can see, or destructive interference, meaning we have the minimum intensity we can see given the conditions, or something in the middle? Now, just to simplify the discussion, let me assume that this incident angle is nearly 0. We refer to this as an assumption of nearly normal incidence. Now, this is not a necessary assumption. It's only that for a short video, this simplifies the geometrical construction as much as we can. Notice that I didn't make the sketch exactly with 0, because otherwise there would be no way to recognize the different waves that we are interested in. And so here now the key point. Those two waves get to this region from the same source through different paths. So we will have interference. So what's the pattern? So for the purpose of this introductory video, I would like to just write down the conditions for constructive interference and then recognize the ingredients and discuss them. Now in a future video, I would like to go deeper in the math and do a more rigorous and clean derivation of the same result. Now, let me write down the condition. Now, just to fix our notation, let me call lambda the wavelength of our incident electromagnetic wave in air, so mostly equivalently in vacuum. Now, the condition for constructive interference is as follows. 2n multiplied by the thickness of our film. Let us assume the simplest form of the simplest geometry. Let me call the thickness d. So here we will have this value of the thickness, this must be equal to an integer number plus 1/2 times the wavelength of the radiation. Okay? So this is the key result for constructive interference, where this m is can be equal to 0, 1, 2, or so on. But just for simplicity, let us focus on m equals 0. So this means that this quantity 2nd must be the same as 1/2 of the wavelength, or like with some other integers, the situation will change a little bit. Now, we have a few minutes, so I have no time to go over the rigorous derivation using plane waves and so on. But we can illuminate, we can give a sense to the core ingredients. So we have the distance here. Notice that 2d is under the assumption of normal incidence. 2d is just this extra path that this second wave needs to cover before it joins the other wave on this side. And that's a very important first point. The second point is this reflection here, which is different from the one down here, because from the theory of reflection, we know that when light moves from a medium with smaller n to a medium with larger n, there is a 180-degree change in phase. And that's important, because if you think about the sinusoid, a 180 degrees change in phase corresponds to a shift by 1/2 of the wavelength. And that's exactly the ingredient that we have here. And now, the last key point to remember is that the wavelength of light inside the medium here will be equal to lambda divided by n. This is a fundamental result from the propagation of waves in dielectrics, in mediums in general. Okay? Now, if you're familiar with interference, you would recognize what we call the optical path. But it's very interesting to just have an intuitive sense. The two waves are together. When they are together in the incident, they come from the same source. And then they go through different paths. One of them simply undergoes a 180 degrees phase change. And that means, or corresponds to a shift of half of the wavelength. The other one will need to go back and forth through the distance d, to cover a distance 2d. If you put the two things together, you recognize that they will interfere constructively if this condition is satisfied. And of course, you can have multiples, so that's the reason for this m here. So now this is the essence of the phenomenon. The rest would be more detailed mathematical derivation. Before I finish, let me comment on a few interesting things here. Notice that there is a dependence on the thickness. So if the thickness is uneven, it keeps changing, then you will have nice interesting patterns there. Now, Newton's rings, pretty famous, are exactly that. Notice that it depends on the wavelength. That's also very important. If you are sending a beam of white light, the different colors will behave differently. So that's why bubble of soaps are so nice and color. Finally, and this is more a technical observation, if here instead of air you have another medium, then you need to pay attention whether the refraction in the sphere is even bigger than this one, because in which case this will become the destructive interference. But if it is air, then for the destructive, you just need to remove the 1/2. Now, that being said, I thank you for your attention. In the next videos, we will do a little bit more maths to be more rigorous. But the key ingredients are those two. A phase shift, so half of a wavelength, displacement in a sense, and a back and forth. It's as simple as that. Thank you very much.